in our discussion, we realized that we see a lot of students who want to be entrepreneurships, who want to go and join startups, and some of you might do a startup. And I see a lot of students interested in mathematics, and I see a lot of students interested in CS. And I saw that the talk that he probably is going to do today is going to link all these aspects: mathematics, CS, AI, problem solving, entrepreneurship. Okay. Then I said, when he said this, and he says, how soon can you come and give a talk to our students? So, with this brief introduction, I give that stage to you.
Yeah, thanks, Vijay. I remember this class reminds me of being back in my PUC days, studying for entrance exams. Unfortunately for me, there was no IIT coaching center in Mangalore itself. There was someone called Mr. Kedilaya in Manipal, and I had to go there 3 times a week to take classes. I guess this is something that I would have loved to have when I was studying for my entrance exam. A short background, I studied in NITK, mechanical engineering. I worked after that at Bajaj on the KTM 125 project. Bajaj had just acquired an Austrian company called KTM. They were kind of confused because KTM only made those big bikes, 700cc, 1000cc. How do you get a smaller version to Mangalore? Sorry, not Mangalore, to India. And that was a project that I was part of. I did that for 2 years. And then decided to do my higher studies in a place called Michigan. Very cold, that's all I can say. I studied something called as operations research, which is mathematics, as Mr. Vijay explained. How do you apply mathematics to the industry? So that's one of my favorite topics. I'll try to speak as much as possible about that during the talk. After Michigan, I worked in the industry. My first job was for an MIT professor who was doing research in transportation. So how do you take his research again and apply it to the industry? So you can see the theme here. How do you apply something that you study here and apply it to the industry? So we'll weave that theme throughout the talk today. Fortunately, unfortunately, that company was acquired by a larger company. I really didn't fit in because I think inside me there's that entrepreneurship spirit, and we'll talk about that as well. So started my own company in 2020. I've been doing that for 4 years. The company name is En route. We take mathematics, apply it to transportation and logistics. Again, I'll leave time at the end and also maybe at the middle to ask your questions, so if I skipped anything. But I want to keep it short because we don't have much time. We have a lot to cover. So that brings me to today's talk. So what are we going to cover today? So we'll cover mainly 2 topics. One is AI. Everyone's talking about AI these days. We'll talk about the history, applications, the current state, and the future, and finally how you can be involved. All right. The next topic is startups, a topic very close to my heart. We'll talk about how I got started, maybe, and then a few tips and how you can start the entrepreneurship journey right now if you'd like. Any questions or anything that you'd like to ask before we start? All right. Let's start with the AI talk first, okay? I think to begin talking about AI, we need to talk about like what is AI, right? How do you define AI? And if you ask 10 different people what is AI, I'm sure you'll get 10 different answers. It means different things to different people. For some people, it might remind them of like the Terminator movie, like robots coming and shooting everyone. Whereas for other people, it might be a chatbot where you can talk to it. So if you now go back at history and see how people have tried to define AI, there was a great mathematician called Alan Turing, and his definition, I think, is kind of generally accepted as what AI should be. And his definition was kind of simple. He asked, if there's intelligence, how do I take it to computers or machines? And how can I make machines think? So, but defining think, what is thinking is a harder problem than you expect. So his definition was, can we build a machine that can fool another human being to think they are another human being. And the experiment is kind of simple, all right? So imagine you're a human being C, and then you're standing behind a wall separated by a partition, one for a computer and one for a human being. And you submit a list of questions to a computer and to a machine. And if you can correctly guess every time if the computer, if it's a computer and this is a human, then you're good. Then the computer is not at the level of humans yet. But if the computer is able to fool you into thinking it's a human, then you're basically the computer has passed what is called as a Turing test, and it has artificial intelligence. That definition slightly changes over the decade, depends on again people you talk to, but I consider this a pretty good definition um, of what AI is. If a computer can pass a Turing test, then we can assume it's generally intelligent. Um, Nowadays, I think with ChatGPT, how many of you have used ChatGPT? Oh, everyone. So teachers at the back, I guess it's hard to grade now with ChatGPT. That's what I keep hearing. But it just shows that computers have started beginning to fool humans, thinking that it's a human. If you're interested to learn more, I have a recommendation down here of the book, the Enigma, or there's a movie made based on the book called The Imitation Game as well. So Alan Turing happened to be like a code breaker that helped Britain or UK win the World War. It's a very interesting movie, but study first, then movies. Okay. All right. So this is great. Now we have science. This was back in the 1950s, and now in the 1960s, scientists start beginning to work on how do you actually build artificial intelligence. So there were a few attempts by different groups like MIT, Stanford, Caltech, primarily. This was ELIZA, which was like 50 years ago, a ChatGPT. They were trying to build a chatbot where you can ask it questions and it was trying to answer you what it thinks. The problem was the way it fooled humans for a little bit was by repeating essentially the questions that the human gives it. So by the fifth question, you'll realize, okay, I'm not talking to a human, I'm talking to a machine. The next one here is Shaky, which is this robot. It's not like Terminator or any of the cool looking robots right now. But this was an attempt, again, to make a robot understand basic instructions. So you could ask it to pick a box. And the thing is, it did actually those tasks, but it took forever. So for example, if you asked it to pick a box that's halfway around the room, it would take about 6 hours to accomplish that task. And the reason is computing power. So the brain of this robot had less computing power than the calculator that you use. I'm not even talking about like the scientific calculator. It's like those basic addition calculators that you have right now. So it didn't get very far. But again, strides, you make incremental progress. The final thing, there are other attempts as well. And I mentioned this last MIT Summer Vision project. So this is an interesting project because in the 1960s, the professors at MIT said, okay, this summer, when we are not teaching students and we have time for ourselves, we would build a system, AI system that could identify objects. And the objects were not very complex either. It wasn't like cat and dog. It was like box versus triangle versus a square and so on. But what started out in 1960s, which was thought to be like a 3-month summer project, was only solved like 10 years ago. So it took 50 years to solve this particular problem. Why do I mention this specifically? I think it goes back to what Mr. Vijay said about entrepreneurship or startups. So you think you'll solve a problem, and these are smart people trying to solve a new problem that has never been solved. And it took them 50 years instead of 3 months that they originally planned. So that's the way startups originally work. So you might choose a problem to solve, but it can take you way longer to solve, because this is not when you do startups, and I'm going a little ahead. When you do startups, it's no one gives you a playbook and says, okay, this is how you run a startup. All right, you cannot go to school for 3 years and build a successful startup. If that existed, not more people would be doing companies. So these are hard problems, and hard problems require time to solve. They might take forever. They might be unsolvable, but that's the nature of the beast that you're dealing with startups. Um, Skipping ahead, I'll skip a lot of history because there's a lot to cover in a few minutes. When people look back and said, why cannot we solve the artificial intelligence problem? The core of the problem was every time they tried to solve this problem, it was uh, solved using explicit programming rules. So, for example, let's talk about the vision project. So, a vision project is essentially computer vision. Can you tell a computer to recognize a cat versus a dog? Now, if you think about how you would solve it, and I would almost take a moment to think yourself, how would you identify a cat versus a dog? Like, for example, if it has pointy ears and whiskers, then it's probably a cat, and four legs and so on. But what happens if the cat is facing the other way where one ear is covered? So would you write new rules of saying, okay, if it's facing the other way, then it has one eye and one ear? There are so many cases, even for small, easy tasks that we take for granted, it's really hard for computers. And any attempts to solve the artificial intelligence uh, pro- uh, problem using explicit programming like if and then rules tended to be a dead end, and we couldn't get too far. But no hope was lost because they created something very, very interesting in a few years. And how many of you are aware of neurons in our brain? All right, almost everyone. So by the 1960s, people realized that the way to actually, if you want to have intelligence, you probably have to look at human beings and say, okay, this is how our brain works using neurons and neuron connections. So can we do something instead of explicit programming? So that's when they started this concept of machine learning. And machine learning is something that we'll spend a little time just to give you a flavor of how artificial intelligence works. All right. So you're familiar with neurons. It has dendrites, it has the soma, which is like the processing thing, and then axon. And what scientists started creating is a mathematical version of what's in our head, a neuron, and that's called a perceptron. All right. Uh, Keeping it simple, what a neuron actually does is takes a bunch of inputs, and these can come from either other neurons or it can come from our sense organs, but it doesn't matter. It takes a bunch of inputs, does the calculation here, and then computes an output, which is either a yes or a no, or like binary, high or low, on the other end. So that's essentially what a neuron does. So bunch of inputs, does some calculation and says yes or no. It's essentially a decision-making machine. Any questions? I know this is a lot to cover, but I want to go slow. Good. Okay. So mathematically, we'll do something similar, where x, y, and z or whatever is there are a bunch of inputs. Okay, x1, x2, and so on. And then there are weights to each input, and then there is a computing part. And this computing part can be anything. We'll come to that as well. And finally, it gives an output saying, okay, yes, high, low, or one, like in binary, or low, no, and so on. Good so far? Okay, we'll go over a quick example because this is like the fundamental thing of artificial intelligence. Uh, a bunch of these put together make all the models, the ChatGPT that you talk about, and so on, are basically a bunch of these things put together in a certain way. Okay. All right. So there's at least when growing up, there was always a person in my class who likes organizing parties. There would be no occasion. It would be like, okay, let's have a party today. And imagine in your brain you have a neuron that decides whether I attend that party or not a party. Okay. And what would be some of the decisions deciding whether I attend this party or no? Okay. So one of them would be, okay, is it on a weekday or weekend? If it's school or not? Are my best friends going? And do I have homework? All right. I think you can relate to some of these inputs. And then you decide, okay, if I'll come to this in a second. You decide if all those factors are favorable, I'll probably attend the party. If those are non-favorable, I would not attend the party. Okay. So applying this to a perceptron, let's say input number one is a binary variable. So you can see here, it's again inputs are binary, 0 or 1. Okay, and the output is also binary. Just keep that in mind. School night, yes or no. Best friends, yes or are my best friends going? Yes or no. And homework going. And let's say for now you say the decision is 1 point. I'll just get to it in a second. If at the end of the day, if the score is +1 or more, I will attend this party. If it's less than less than 1, I will not attend this party. Okay, let's assume this is on a Saturday and my best friends are going. I do not have homework. So what happens is Saturday. So is it on a school night? No, 0. So that's 0. Are my best friends going? Yes. So +3. And do I have homework? No, 0. So the score is 3, and my decision was 1. So I probably will attend the party. Does that make sense? Cool. But on the other hand, if it's a Wednesday now, and I have homework, I would have -3. -2 +3. This -1, and then +1, and then -1 again, which is 0. So 0 is less than my threshold of 1. So I'm probably not going to the party. Clear about perceptrons? So if you understood this, this is essentially how perceptrons work. So the only thing that I haven't explained in this slide is the learning part of it. All right. So let's say in the first example, you actually end up going to the party, and then you realize it's a bad idea. You shouldn't have gone. You should have stayed home and studied. So what you do is next time you either increase the threshold and say, okay, it needs to be 3 or more for me to make yes decision, or I'm going to adjust the weights. And this is essentially a feedback loop, and that's essentially how learning happens. So every time you make a decision, you update your weights based on that decision, and over time you'll hopefully get better at it. You'll get more intelligent. Cool. Okay. All right. So we are at this stage where we are still in the 1960s. We have okay. So okay, we are still in the 1960s. We have early attempts at artificial intelligence that are fooling nobody, and we have a perceptron. Why didn't artificial intelligence actually take off in the 1960s? Why did it have to wait another 50 years for artificial intelligence to take off? The answer lies in the previous comment that I made about the robot, which had very less computing power. The computing power available in the 1960s was not enough to train these models. So essentially, they put a bunch of these perceptrons together and now try to train it on real world data. That training process is very computationally intensive, and the computation required to do that wasn't available in the 1960s. What changed was in the 2000s, gamers started getting better games. And because, how many of you play video games here? So you're familiar with graphic cards? All right. So as games became more and more realistic, the graphics cards became more and more powerful. And there were researchers, I'm sure they were also gamers, who realized that the game, what graphics cards do to generate visuals is the same kind of mathematics that the perceptrons use for training. Does that make sense? So, and I'll skip a little ahead. So the maths that's used for training is essentially matrix operations that you've done. Like matrix multiplication, for example, is a very, very big component of how neural networks are trained. And if you're thinking, why am I doing this homework of matrix multiplication and it's of no use, you're wrong. So it is very useful, especially to AI. Matrix multiplications are required for generating visuals that you see in games, and it's the same thing that you use for training artificial intelligence models as well. I'll stop here. Good so far? Okay. Yep. So a lot of these calculations. Now I think there's one other thing where if you're familiar, there's a GPU, which is a graphics processing unit, but also there's another thing called as a CPU, which used to be the central processing unit if you're taking your computer classes. A CPU is like a very smart person, all right? It can do very complex math, and GPU is like an average person who can do ordinary math. Um, the difference between a CPU and a GPU is that GPU can is like having a lot of average people doing simple math, whereas CPU is like a smart person doing very complex math. And neural networks or artificial intelligence training requires more of the latter kind. It requires real simple calculations, but a lot of it. I just went over this. The example is, let's say you have to multiply 1,000 numbers. If let's say I pick the smartest guy in this room, I know there are a lot of them here. I pick one on average and give you 1,000 numbers to multiply, versus I give one number to multiply to the whole class. Which one do you think is faster? So that's essentially what's happening versus CPU and GPU. Now, because GPUs were getting better and better, the artificial intelligence models were getting better and better. And somewhere like 10 years ago, 15 years ago, is when we started getting models that actually started fooling humans into thinking this is another human. They're starting to pass the Turing test, which I mentioned. I'll give you a couple of examples which I think are relevant. In the 1990s, most of you were just born then, I guess. Uh, there was uh, it was thought that computers can never beat human beings in when it comes to the game of chess. But IBM built built like a computer called Deep Blue, which beat Gary Kasparov at chess. So that was like a inflection point of now you train these perceptrons. I gave you the party example, but imagine those perceptrons are taking weights from squares in a chessboard and weighing each position accordingly and learning every time. They are adjusting their weights by every game. So by the time they've played a million games, they're very smart. Okay, those are the kind of models that beat Gary Kasparov. Then people. So I think I'll take a step back and talk about human psychology. So imagine going to a magic show and seeing like a trick that you've never seen, someone cutting the head off and someone joining it and so on. So you know what the tricks that I'm talking about. It seems amazing, okay, the first time you see it. But let's say the magician takes you back to the back room and says, okay, this is how I did the trick. And then you'll be like, oh, this is how it's not magic anymore, right? So that's essentially what's happening with AI. So the computers beat the game of chess, and they're like, oh, this is how you did it. Oh, this is not artificial intelligence anymore. The next thing I think what they said is, chess has 64 squares, and then there are only moves that are constrained. Like you can only make certain moves. So it's a simple enough problem. So it's not artificial intelligence yet. I don't remember the exact year. I think it's 2015. There was another game which is a strategy game like chess. It's called Go. If you have, it's a board with white and black squares. It's a very interesting game. It's much more complex than chess. And Google built a model called AlphaGo that beat like the world record holder in Go. And at that point, people knew something was different. This is something that is truly magical. Fast forward 3 more years, Google built another model that beat. That beat a gamer. So we are talking about games. There's a game called StarCraft, like a real-time strategy game, RTS game. Too old, yeah. And they were playing. They were beating the best players in computer games. At that point, people are like, okay, there's something happening. And then you have ChatGPT, and now it feels like it's artificial intelligence is here. I think that's like the brief history of artificial intelligence in 5 more minutes than I thought. Okay. Okay. So let's given that we know the history and where the current state of artificial intelligence is, we'll talk about how it applies to you. Okay. So first thing is, like I mentioned, matrices are not just homework. Okay. We talked about perceptrons. We talked about like neurons and so on. At the end of the day, everything that's powering it is matrix multiplication. And the broader theme here is something called as linear algebra. Linear algebra is how computers do math. All right. So remember, every time you're thinking about matrix and cursing your teachers, maybe, and it's not for vain. Okay. And this is one of those things. Like personally, I felt that whatever I study will never come into use, so on. And the thing is, once I look back, I can see how the things that I studied fit in many different ways. So you never know how it fits. You can only see how it fits looking back. Okay. So Steve Jobs, I think, calls it connecting the dots looking backward. So I think that is very true. As long as you understand the foundation, you understand the fundamentals of why that is, I think it will come in handy to you in the future. And another thing is learning how to think. So AI didn't exist when I was doing my engineering. Okay, this was I'm dating myself here, but it's okay. So um, it's um, AI was something that happened like maybe 5 or 6 years after I graduated. Now there was no way for me to learn AI in school, but since I studied maths in school, like statistics and calculus and probability, it wasn't too hard for me to understand what's going on. So that's a way I think I would recommend you to think is if you understand the fundamentals, they'll come in handy at some point. And also, let's say it's something that you didn't learn in school. The very fact that you can read a book and understand the concepts and apply it, that skill will be really handy for you, no matter what you choose. Startups, entrepreneurship, otherwise, it's going to come in handy for you. One example, so I've been saying, okay, matrices, everything is matrices. I'll go over one concrete example and then we'll conclude this part of the presentation. All right, so we talked about image detection as one of those artificial intelligence tasks. To recap, if you show a computer a picture of a cat versus a dog, the computer should say, this is a cat, this is a dog. How does it do that? So if you take an image and think about how it's stored in a computer, it's all zeros and ones, and that's not saying much, right? So what it is every what they call is a pixel. If you look close enough, there's a square here in the screen. Every pixel is made up of three values: red, green, and blue, which correspond to the red, green, and blue cells in our eyes. So every image, every pixel has, okay, this is 50% red, 75% blue, or 0% green, or something of that sort. So every pixel here stands for some RGB value. And let's say a 1080p HD image has 1920 into 1080 pixels. And each pixel is made up of red, green, and blue. So if you look at the number of numbers, there are about 6 million numbers, right? 62 lakhs. And each one of them, for the AI to think, has to take one of those numbers, multiply it with something else. So it's a lot of multiplication. So uh, uh, even though you don't see yourself doing these large numbers, knowing how matrix multiplication works can definitely come in handy. So finally, I'll conclude with this slide, this section as well. Is if AI is already there, why should I be interested in AI? So I think AI is generally there, but there are problems. Okay, so first thing is it's very energy intensive, and I don't have to talk much about sustainability and energy here. You can see the structure here; it's carbon neutral, and you focus a lot on sustainability. So AI today is very, very power hungry. It takes a lot of energy. Researchers are working on how do you make it more efficient. That's an open problem. Maybe when you graduate, it's still an open problem. I think it's going to be a open problem. The second thing is cost. We talked about GPUs. If you've built your own computer with GPUs, you'll realize it's very, very expensive. How do you build cheaper hardware? The other thing is sometimes when you ask ChatGPT, it gives you gives you answers confidently, but those answers are wrong. We call that like hallucinations. Oh, you're familiar with that, and no one knows why, isn't it? So how do you reduce hallucinations? The last thing is, how do you understand how the AI makes decisions? So I mentioned that we talked about how neurons and artificial intelligence have parallels, but it's not exactly the same. No one really understands how artificial intelligence works. So those are open research topics. All right. So I talked about this. To solve those problems, you need linear algebra. You need calculus, especially gradient descent. If you know about it, like limits, probability, statistics, and so on. So I wouldn't go into each one of these, but trust me, you would need all of these to be doing research in AI. All right, so that's I'll give a small break here just to ask questions. So that's our section on artificial intelligence. Okay. Okay. So the question is why probability is required for AI. I'll give you an example. Again, going back to the vision example, let's say this is a cat, image of a cat, and this is an image of a dog. If you think about yourself of given an image, how do you identify a cat or a dog? Uh, for you, it seems very natural to say, okay, this is a cat or a dog. But inside your head, if you look closely, especially if it's a small dog and a big cat, when they become very similar, you make a decision that this mostly looks like a cat and this mostly looks like a dog. So translating that analogy to the computer, so the computers basically tell you there's a 70% confidence I think this is a cat, and only 30% confidence or 30% chance or probability that this is a dog. And then it says, okay, this is 70%, this is 30%, I'll choose the 70%. So knowing how it can come up with 70%. So how did it come up with 70%? That's the probability calculation it's doing in the back end. So based on everything that it has seen in the past. It's like, okay, 70% of the time I got it right. So that's the intuition behind using probability. Does that answer your question?
Yes.
Okay, perfect. Good question. What else? Please.
So recently, Pfizer has released a new ad for make AI mediocre.
Okay.
Why they even do that? But they say that AI learns whatever is there, like everything on the internet.
Okay.
So how do we restrict AI to only like write stuff so that
Right,
AI
sir.
doesn't become corrupt?
Okay. I think wonderful question. This goes into a broader topic of ethics and AI, isn't it? There are AI applications that are used for wrong. Like an example would be someone impersonating you as coming from the bank and writing an email, very convincing. It goes into the broader topic of AI. So I think there are. So here are my thoughts into how do you make AI incorrupt. Good one, yeah. So I think there's so before even I give a solution, it's a classic case of like being a knife, right? A knife can be used. Like it's you can use it to make your dinner tonight, or it can be used to harm people. AI is sort of the same way. So how do you regulate it? So one thing is if you see all these big companies, they have like ethics boards which say this is the data that you train on, and this is the kind of this is the kind of responses that are acceptable. You won't answer questions that are not acceptable. So I think that's one way of doing it, of setting like a governing body that regulates the AI. The second approach, which I think is better, is um, something called as open source. Open source is basically someone who creates an AI model says this is how I've created it, and if you want to create your own, this is how to do it, and they give you all the code to do it. And then it's your choice of what you want to train it on. So if you do not want to use a corrupt AI, then take an open source model, train it on stuff that you only want, and then you have a bot that is using that is non-corrupt. Okay, good question. So what else? We'll take one more question and then go on to my next favorite topic, startups. Anyone? Someone here? Yes.
What is your experience with the AI, working with it? What did you do?
Okay. Wonderful question. Okay, so I run a AI company as well, and AI has very different applications. So I'll talk about two applications of AI that I use in my company. So I said we talk about uh, we work on transportation and logistics. And think of it like one of the use cases for my product is how do you plan a delivery route for a van that is making deliveries today? So imagine you bought something from Amazon. It shows up in a van or a truck. Somehow someone has decided to stack the orders in a certain way, and how do you stack them in the right place? And also, if you have many orders, how do you decide which truck you should go on? So those are both hard problems. The way we apply AI, one thing is for traffic. Okay, so when you plan loading the truck in the morning, you don't have traffic real time. So you basically have to study patterns in the past. What was the traffic like on Wednesday, the past week, and the week before that, last month, and then try to make predictions about traffic today, even before your truck leaves its warehouse. So that's a very good case of machine learning. The second use case is businesses come with inefficiencies. It would be nice if computers talk to each other, especially when you're talking about two different companies interacting with each other. So, for example, let's say I want something to be moved by another company. So I have something to be moved, and another person has a truck. So the way it works is someone writes something on paper, or someone sends an email, and then the other company has to take time understanding what's written and then translating that into orders. So something like ChatGPT, we have a custom version which takes all those orders and tells them this is exactly what you should be doing, without having to spend time uh, uh, reading through each line and saying, okay, this is what exactly I should be doing, this is what I should not be doing, and so on. So those are two applications. We do more as well.